Hi, I'm Alexander Kukushkin, Principal Engineer at Microsoft. Today I'll talk about PgQ, Postgres extension implementing queue that has been around for almost 20 years. I'll explain why it outperforms skip lock-based design and how to use PgQ on cloud-based Postgres. Let's dive in to PostgreSQL queues done right with PgQ. And agenda for today's talk. Why one want to run queue in the database? Why not to use external queue? Then, like how people naturally approach implementing in database queues using select for update skip locked. What are the problems and disadvantages of this approach, and how PGQ solved this approach solved these problems many years ago. Basically, I would like to reintroduce you a PGQ extension. And finally, we are going to discuss how to run PGQ on managed cloud services, which don't support natively this extension. All right, so why why engineers want to run queues inside the database? Why not to use something external like Kafka, RabbitMQ, or you name it? There are many different technologies that allows you to running queues outside. First of all, because it's totally new technologies, they have their own learning curve, sometimes very steep, and you of course need to run separate hardware like to external queues. And so on and so forth. Unfortunately, it's not very easy to have consistency between the database and external queue. However, when you have a queue inside the database, you can insert events into the queue in the same transaction and be fully consistent and atomic. After all, database is a single source of truth for your application. Um, Natively, naturally, people tend to implement something very simple, like presented on this slide. They create a very small table, very simple table with just 3 to 5 columns. One of them is a primary key, which is used to refer like to unique events in the queue, like timestamp field and the message which contains the event. Inserting into such queue is simple insert statements. You just insert messages from one connection or from multiple connections. Like sounds very simple. Consuming from such a queue a bit more complex. Very first thing that people usually do, they start a transaction and use a select for update ordered by identifier primary key with some limit, and they use skip for update skip locked. Why they want to use for update skip locked? Because the people want to consume events from multiple connections, from multiple applications, and this way they split jobs between them naturally. Like once they selected a certain number of events, they process them, and for successfully processed events, they remove them from the table by using primary key, the ID column. And at the end of transaction, they commit. If some events are not processed, then they will be available for the next time. However, there are certain problems and disadvantages. Of course, such approach has advantages too. First of all, it's extremely simple and easy to implement. You get parallel consumption of events out of the box, but disadvantages are much bigger. Like you keep transaction in progress while processing events. It means that while you're processing events, you accumulating more and more the tuples on the table. Then, like by doing select for update and by removing rows, you also introduce the tuples, and it requires some aggressive vacuuming of the queue table. In the situation when you have a spike of events that being inserted into the queue table and slow consumers, you have quite fast growth of the queue table, And while you are processing events, like with not enough speed, you accumulate more and more tuples in the table, live tuples and dead tuples as well. So at the end, you get some uh, loop of problems. Like the bigger queue table becomes, then the slower consumers will work, and so on and so forth. And problem will be problems also will be amplified by some other long-running transactions in the system. For example, if someone is doing sort of OLAP queries, it will also prevent vacuum from doing its job. So people try to fight this problem. And what they usually do, they extend qtable by a few more columns. One of them is a column with the name VT on this slide. Uh, so VT stands for visibility timeout. It says when events should be processed, like at what time. And they also want to limit number of retries to process the event. And it is being solved by introducing yet another column, read count. And as you see, we introduced also a new index on VT column, because sometimes for Postgres it's much faster to select events from this table by using the index on visibility timeout column. And our select, previously very small and simple, becomes CTE. Now we have to do additional filtering on visibility timeout. And after selecting some number of rows, we update them by setting visibility timeout somewhere in the future. This is the time when event is supposed to be retried next time if it wasn't processed successfully. And we also increment read count. Um, so once we selected some number of events, we process them, and after successfully processing, we remove them from the queue table. Uh, Seems to be a bit better, because now we don't have to keep transaction in progress while processing events, but at the same time we started doing yet another update on the table. So originally we just inserted event into the table, then we did at least three updates, like select for update, actually update the row, update, also update the row, and insert the new one, and delete also updates a row. Uh, um, that's quite a bit of overhead in terms of writes. Uh, we also introduced a new index on visibility timeout column, which effectively disables hot updates optimization. And Postgres will not be able to optimize for hot updates, and you will get not so good space utilization. And index on visibility timeout may also confuse planner, because planner may at some moment think that it's more beneficial or faster to use column, so visibility timeout index, rather than primary key. And queries that were taken just a few milliseconds, queries on the queue table, may start taking 10 seconds, like 20 seconds, and so on, which is just a few orders of magnitude slower than it's supposed to work. How can it be improved? So in order to fight with bloat on the queue table, it's recommended to partition it, or just create some uh, more than one table and switch between them when writing and consuming events. Uh, when events are fully processed from one partition, uh, it could be just truncated or dropped, and because like new partitions will be used. This way, we eliminate the need to fight with the bloat and use something like pgrepack or reindex concurrently, or pgsqueeze, or something, or repack concurrently, which will come into new Postgres 19. Um, ideally, we should avoid doing so many updates and deletes on the queue table. But how we can actually remember which rows were processed? It's quite simple. We can keep a pointer to last identifier which has been processed. And when we selecting from the queue table next time, we just in the select request rows with identifiers which are bigger than the last processed ones. When processed the next bunch of events, we just update last identifier in some other table. Like we just keep pointer, and in this case we need to think something about retrying events, and it could be solved by reinserting them into the queue table. So, or instead of reinventing the wheel, we can just use PgQ extension, which does it natively since the very beginning. PgQ is quite old extension. It exists since 2007 publicly. It was part of SkyTools back then. If you are not familiar with SkyTools, it also contained PL proxy that implements sharding, and PG bouncer tool that implements connection pooling. And like, it's quite surprising that many people know PG bouncer but never heard of PGQ. Packages for PGQ are available on PGDG, like for Debian-like systems or Red Hat-like systems, like dep and RPM packages. PGQ implements event handling based on snapshots, which is fully transactional, and it employs batch processing optimization. Interface of PGQ is like fully SQL. It provides a few functions to insert queues, to process them, and so on. PGQ supports multiple producers per queue and multiple consumers per queue, but consumer will see all events that are coming in the queue. How can it be installed? You just use your package manager, like in your Linux operating system, and you need to install PGQ3 package, and on top of that, unfortunately, you need pgqd package. Without pgqd, PGQ will not do anything. PgQd, it's a maintenance daemon that responsible for like some tasks that happens under the hood. All right, so once packages are installed, you just need to create extension. And once extension is created, you can use very simple SQL API to work with queues. You need to use create queue to define a queue, and you can symmetrically drop the queue by using drop queue function. In order to consume events, you have to register consumer. And consumer will see events on which were added to the queue only after it was registered. To insert events, you simply use insert event function. It just adds event to a queue table. But to consume events, you need to form a batch, which is done by using next batch function. This function returns batch identifier, which later should be used in get batch events function to actually fetch events from the batch, and finish batch function will close the batch and discard like processed events. So let's zoom in and look into what's inside PGQ extension. There are a few configuration tables. We will take a look closer at these configuration tables a bit later, but the event one table, it's a table which was created by create queue function. So in fact, we have not just a single table, but one parent table and three child tables. PGQ isn't using table partitioning. In fact, it's using table inheritance. And it's not because table partitioning did not exist almost 20 years ago, but because those tables are just used independently of each other, and PGQ inserts and selects directly from every child table independently. So in the PGQ table, we have a Q name, which reference a Q table, and it also defines that we have 3 child table for a given Q. And every 2 hours, like showed here on the slide, Postgres will, so PGQ will switch to a next event table, like while doing inserts. Okay, so and if we look closer at one child table, you will notice that it has just a single index on transaction ID column, and you will also notice that it disables after vacuum. So why one should disable after vacuum for the table? It's very simple, because we don't expect any updates or deletes on this table. Therefore, it does not need to be vacuumed. And more important, like after 2 hours and or like after at max 4 hours, this table will be truncated. Therefore, we don't want to don't want to waste IO operations by doing unnecessary maintenance on this Q table. Okay, so now I would like to discuss a little bit details about how batch processing works, and like why do we need pgqd process. So main responsibility of pgqd process is to produce ticks. Ticks are inserted into pgq tick table. It's on the right side of the slide, and every tick contains transaction snapshot, which was at the moment when tick was created. And batch is defined as all events that happened between 2 ticks. So on the left side of the slide, in the bottom, we see batch number 1, which includes all events between ticks 1 and 2. So, and when we read batch events, we just call get batch events function, and it returns events. But what happens under the hood of this function? Under the hood, it actually uses dynamic SQL and selects from a single event table. In fact, sometimes it may select from 2 more event tables, in case if it can understand that some ticks were stored, so some events are stored in a different child table. So in this case, the union all will be used. What's interesting here, we are not just searching for events between 2 transaction IDs, but also doing some filtering using TXID visible in snapshot function. So why is it important? Because it may happen that transaction ID like that falls into this specific range wasn't yet committed at the time when the next tick has happened. So that's so PGQ is using MVCC Postgres MVCC implementation to find events. All right. So and when we finish batch with PGQ, so we call finish batch function apparently, and the only thing it does, it just updates subscription by moving a pointer, like last tick pointer, which is on the right side of the slide. So it was before like pointing to 1, and now it points to 2. So next time when you will create a batch, it will start from tick 2. Okay, so how can we run PgQ on managed services, because none of the most of managed cloud providers that offer Postgres don't support PgQ. Does it mean game is over and we cannot use it? No, it's totally not. So PgQ is mostly implemented in PGSQL language, which is a trusted language. There are just 4 functions that are implemented in language C. Those functions exist only for performance reasons. However, starting from year 2016, so almost for 10 years already, there are alternatives available which are implemented using PGSQL. And to use these functions instead of C functions, we just need to build PGQ using make PL only. So we clone PGQ from GitHub, we run make PL only, and it produces an SQL file which you execute inside your database. And when this file is executed, you get full list of functions that define PGQ extension. And you can use it the same way as it was, as if PGQ was created using create extension. Okay, so if you remember, like PGQ requires a PGQ daemon uh, where we can run it. Like if we want to use PGQ on managed services, we have a couple of options available. First of all, you can run PGQD on some virtual machine. Like it hasn't be very powerful. Something very cheap and small is enough, because it's not running any heavy calculations. It just need connect to a Postgres and run PGQ maintenance function from time to time. Or the second option, you can hack your own solution on top of pgcron. Pgcron, it's also a Postgres extension that implements cron-like jobs on directly in Postgres. And if you look at pgcron GitHub, you will find that it is supported by at least 15 cloud platforms. And only one cloud platform does not support PGQ out of this list. I'm not sure if there are people who still use this cloud platform nowadays. To understand how to re-implement PGQD using pgcron, we need to know what PGQ does under the hood. And it does just 3 main tasks. First, it produces ticks, basically inserts data into PGQ tick table. It happens every second by default. Then the second task of PGQD, it handles retries by moving events from PGQ retry queue tables to actual queue. And the third task that PGQD responsible for, it's a maintenance operation. It has to rotate actual child tables and from time to time truncate them based on the configuration. So retries are handled by PGQD every 30 seconds and maintenance handled every 120 seconds. The beauty of PGQD that it does not implement any sophisticated logic in itself. It relies on functions provided by PGQ extension to do the job. So in case of ticker, PGQD just calls a PGQ ticker function, which is already there. In case of retry and maintenance operations, it's a bit more sophisticated, but still under the hood, there are PGQ functions that it will call. But we need to provide some wrappers for these functions implemented in PGSQL SPL PGSQL procedures, not functions. Why procedures? Because we want to commit after every call of the function. So on this slide, you see PGQD retry function, which handles retries by calling PGQ main retry events function in a loop, and it breaks from the loop when the function starts returning 0, what means that all events has been moved from the retry table. And the maintenance function a bit more complex, but still it works in a way that main operation functions returns a set of names, like function name and function arguments, which has to be used when calling a function. Basically, we get list of functions to be executed, execute them, and after every execution, we commit. So this is exactly what pgqd does under the hood. So be careful, don't turn after vacuum off, because PgQ also, like in PGQ, also sometimes may vacuum PGQ configuration tables. Why it was doing this? Because like 20 years ago, there was no after vacuum in Postgres yet, and therefore such task has to be offloaded to some external tools. And as a good citizen, PGQD was trying to do it to solve this problem. And the second issue, like pgcron itself, for every job that executes, it inserts status of execution into job run details table. So this table will grow very quickly because we run ticker every second. So it would be nice to have another cron job that cleans up cron job run details table. Okay, so coming to the end. So to recap, PGQ, it's a great queue for Postgres. It was designed and implemented by real engineers and real Postgres hackers. It does not use skip locked. It does not generate table bloat. There will be 0 dead tuples in the queue table and absolutely no write overhead. Some people claim that PGQ is old and unmaintained and maybe even deprecated. In fact, it is not. It is stable like rock, and most likely it is bug-free. If you look at GitHub, you will find that last commits to PGQ only update README files mentioning that it supports Postgres 17 and Postgres 18 without any changes in code. Unfortunately, documentation for PGQ extension isn't great, or I would say it is absent. You need to do a lot of research on the internet to make it work. However, PL-PGSQL is a relatively simple language, and you can learn a lot by reading PGQ source code and understand how to use PGQ API. Of course, there are some libraries available on the internet that implement PGQ support for Java, Python, PHP, and so on. But since it's a SQL API only, you can implement easily PGQ some libraries for your own for your favorite language. That was it. Thank you for listening. I hope you enjoyed.